Welcome to the English Interactive Quiz, authored by Associate Professor NOUREDDINE HALI. We'll explore 5 chemistry topics: the mole, redox reactions, reaction progress tables, colorimetric titrations, and structure and polarity. We'll also consider waves and signals as we move through the questions and activities. This slide introduces the first theme of the presentation, the mole. It serves as the organizing concept for the material that follows, giving us a clear focus as we move through the next sections and examine how this theme shapes the presentation. Excellent work! Molar mass is the mass of 1 mole of molecules, not the mass of a single molecule. 1 mole always contains 6.02 2 times 10 to the 23rd molecules, Avogadro's number. Keep that distinction in mind. Molecule refers to one entity, while molar mass describes an entire mole. The correct answer is 23.0 grams per mole, or 23.0 d mol minus m. The value 11 is sodium's atomic number, representing its protons, not its molar mass. Remember, sodium ions are safe in table salt, while pure sodium metal reacts violently with water. The correct expression is MCOA2 equals sign MC plus 2MO. Carbon dioxide contains 1 carbon atom and 2 oxygen atoms, so we add their molar masses according to the molecular composition. Excellent work. As a reminder, solid COA2 or dry ice changes directly into gas through sublimation. The correct answer is 48.0 liters. Using the relationship V equals N times Vm, we multiply 2 moles by 24.0 liters per mole. Under the same temperature and pressure, any gas occupies the same molar volume, regardless of its identity. Excellent work applying this relationship correctly. The key relationship is between amount of substance, mass, and molar mass, N equals M divided by M. Equivalently, M equals M divided by N, or M equals N times M. Remember that molar mass is measured in grams per mole. Excellent work mastering this fundamental relationship. The correct answer is 2 moles. First, calculate methane's molar mass, 12 plus 4 times 1, giving 16 grams per mole. Then apply N equals M divided by M. 32 grams divided by 16 grams per mole equals 2 moles. Excellent work, and methane hydrates are sometimes called burning ice. Excellent work. Molar concentration is the amount of solute N divided by the total solution volume V expressed in liters, C equals N over V. The unit is moles per liter or mole/N. Remember, mixing liquids can cause volume contraction, so final volume is not always the simple sum. The key point is that a spectrophotometer directly measures absorbance, the proportion of light absorbed at a specific wavelength. From that measurement, we can calculate concentration using Beer-Lambert's law. The solution's visible color is related to complementary color absorption. Absorbing red light, for example, makes it appear green. The correct answer is a mixture of red and blue. The spectrum shows strongest absorption in the green region, roughly 500 to 580 nanometers. Because the solution absorbs green light, it transmits wavelengths at the extremes, red and blue, so we perceive a magenta or violet color. Excellent interpretation of the calibration curve. The straight line through the origin confirms that absorbance is proportional to concentration, validating Beer-Lambert's law for this system. Remember, this relationship applies to dilute solutions. At higher concentrations, saturation can cause the curve to deviate from linearity. This slide introduces the topic of redox reactions under Theme 2. The title signals the subject we're focusing on here, while the theme label places it within the broader structure of the presentation. The detailed concepts and examples will follow on the next slides. Excellent answer. An oxidant is an electron acceptor. It captures one or more electrons during a redox reaction. A useful memory tip is oxidant captures, reducing agent gives. This electron accepting role is also essential in cellular respiration, where oxygen helps cells obtain the energy they need. In the cow couples SU couples is the oxidizing agent. By convention, redox couples are written ox/red, so the species on the left is the oxidant. SU couples gains 2 electrons and becomes solid copper. This reduction also explains why the blue solution can lose its color as reddish-orange copper forms. The correct half reaction is AlAq plus 3A con plus 3A minus equals sign ALS. Aluminum ions gain 3 electrons, balancing both the atoms and the electrical charges. Notice the equal sign rather than an arrow. It represents a reversible half reaction. Excellent work. You've mastered the formal notation. Excellent work. The correct overall reaction is 2AHG plus AQ plus ZNS equal to AHGS plus ZN2Q. Zinc releases 2 electrons, while each silver ion except 1, so the silver half reaction must be doubled. In the lab, this reaction can even create crystalline silver structures known as Diana's tree. Excellent work. In the half equation Hg2 plus 2 electrons reversibly forms 2 liquid mercury atoms. So Hg2 plus is the oxidant. It accepts electrons. Liquid Hg is the reducing agent because it can donate electrons in the reverse direction. Remember, mercury is uniquely liquid at room temperature, and Hg2 plus exists as a dimer. Great job. A redox reaction involves the transfer of electrons, not H plus ions. The reducing agent gives up electrons, while the oxidizing agent receives them. By contrast, H plus transfer belongs to acid-base reactions. This electron exchange is also what enables batteries and electrochemical cells to produce power. Well done. The key idea is that the maximum extent of reaction depends on both the initial reactant quantities and their stoichiometric coefficients, calculated by dividing the initial amount of the limiting reactant by its coefficient. Don't confuse this with the reactant amount itself unless the coefficient equals 1. For 2.0 moles of magnesium, the balanced equation requires twice as many moles of hydrogen ions. Therefore, the stoichiometric mixture contains 4.0 moles of H+. This ensures both reactants are consumed in the correct proportions, while the reaction produces hydrogen gas, which is highly flammable. To identify the limiting reagent, I compare each amount with its stoichiometric coefficient. Silver ions provide 1.0 divided by 2, or 0.5 moles of reaction capacity, while copper provides 2.0 divided by 1, or 2.0 moles. Silver ions are consumed first, so they limit the reaction. Well done. This is the correct interpretation of the equivalence point. Both reactants are present in stoichiometric proportions and are completely consumed. That means neither the titrant nor the titrated solution is in excess. In some colorimetric titrations, the endpoint color change can occur within a single drop. This slide introduces Theme 3, the reaction progress table. It signals a shift toward organizing reaction progress in a clear, structured format, making it easier to follow how the reaction develops and how its key stages relate to one another. The correct answer is that the extent of reaction X is expressed in moles and increases as the reaction proceeds. It measures how far the chemical transformation has advanced from its initial state toward the final state. Its increase may slow over time, but the overall extent continues to rise. The correct answer is the quantities of chemical species expressed in moles. A reaction progress table tracks how the system changes using amounts of substance, not directly masses or volumes. Any experimental data given in grams, liters, or concentration must first be converted into moles before entering the table. Well done. During a chemical transformation moving forward, reactants are progressively consumed, so their amounts decrease, while products form and their amounts increase. In reversible reactions, products can also reform the initial reactants, eventually creating dynamic equilibrium, even though molecular transformations continue at the macroscopic level. The stoichiometry gives us the key relationships. Each reaction extent X forms X moles of aluminum hydroxide and consumes 3X moles of hydroxide ions. Therefore, the remaining hydroxide is N0OH-3X, while the remaining aluminum ions are N0Al plus minus X. The precipitant is also amphoteric and can redissolve in excess hydroxide. To find the maximum reaction extent, I calculate the value at which each reactant would be completely consumed, 6.0 moles for alpha Q plus, or 3.0 moles for HO minus because its coefficient is 3. We choose the smaller value, so X hand here X equals 3.0 moles, and hydroxide is the limiting reactant. The correct answer is X-carnitine, X-carnitine 10.0 moles. In the reaction, LOH3 has a stoichiometric coefficient of 1, so the amount formed directly equals the maximum reaction extent. Since 2 moles of precipitate are produced, the maximum extent is 2 moles. Well done. For an incomplete transformation, the limiting reactant is not fully consumed, so the reaction stops before reaching its theoretical maximum. The final extent, X sub F, is therefore less than X max. In other words, the extent ratio remains below 1 because equilibrium is reached before complete consumption. Well done. In a complete reaction with a stoichiometric mixture, all reactants are consumed simultaneously, so their final amounts are 0. The final state contains only the products formed along with any spectator species. This balance is essential in applications such as ideal engine combustion, where precise proportions improve performance. To determine whether the mixture is stoichiometric, I calculate the maximum reaction extent for each reactant. Reactant 1 gives 6.0 divided by 2, or 3.0 moles. Reactant 2 gives 12.0 divided by 4, also 3.0 moles. Because both values are equal, the reactants are consumed simultaneously, confirming a stoichiometric mixture. For a stoichiometric mixture, the initial amounts of hydrogen and oxygen must match their coefficients in the balanced equation. So, N0H2 divided by 2 must equal N0O2 divided by 1. In other words, we need twice as many moles of hydrogen as oxygen. Well done. This section focuses on colorimetric titrations, a method that uses visible color changes to help identify a titration endpoint. Under Theme 4, I'll frame the topic around how color serves as the key visual signal in the analytical process. The correct answer is its concentration. Titration determines the unknown concentration of a chemical species in solution by reacting it with a substance of known concentration or by using an instrumental method. This quantitative technique is fundamental in chemistry and also supports applications such as blood glucose testing and drinking water quality control. The correct answer is a chemical reaction, a titrant, and an analyte. Titration determines an unknown concentration by adding a solution of known concentration to the analyte until the reaction is complete. A calibration range belongs to physical, typically non-destructive methods rather than chemical titration. Excellent work. The correct answer is fast and total. A titration reaction must reach completion quickly after each titrant addition, and it must fully consume the limiting reactant to provide an accurate mole balance at equivalence. It should also be unique, without competing side reactions that could distort the result. Excellent answer. In a classic titration, the analyte or titrant goes in the beaker, while the titrant goes in the graduated burette. The burette delivers the known solution precisely, drop by drop, so we can measure the volume needed to reach the equivalence point and determine the analyte's concentration. The correct answer is the analyte or titrant. It is the reactant whose concentration is unknown and must be determined. By contrast, the titrant is delivered from the burette at a known concentration. If that concentration is uncertain, chemists first standardize the titrant before using it in the analysis. At the equivalence point, the titrant and analyte have been added in stoichiometric proportions. Their amounts follow the reaction coefficients, so both reactants are completely consumed together. This is not necessarily when their volumes are equal. The defining condition is the mole relationship required by the balanced equation. At the equivalence point, the analyte and titrant have been added in exact stoichiometric proportions, so both are completely consumed. This is also the moment when the limiting reactant changes. Titrant is limiting before equivalence, while analyte becomes limiting afterward. Equivalence is the precise transition between these two states. This question tests stoichiometric reasoning at the equivalence point. From the balanced equation, 5 moles of hydrogen peroxide react with 2 moles of permanganate. So N0H2O2 divided by 5 equals N0MnO4 divided by 2. The titration is self-indicating. Excess permanganate creates a persistent pink color. The correct answer is a color change in the beaker or Erlenmeyer flask containing the reaction mixture. At equivalence, the last trace of analyte has been consumed, and the first slight excess of titrant reacts with the indicator, producing a visible color switch. Excellent work! This titration uses color to identify equivalence. Before equivalence, iodine remains in the mixture, producing the yellow to brown color seen in photo 1. At equivalence, all iodine has been consumed, so the solution becomes completely colorless, as shown in photo 2. Starch can make this endpoint even sharper. This slide introduces theme 5, structure and polarity. It signals a shift toward examining how elements are organized and how opposing qualities or directions may shape that organization. The focus here is the relationship between structure and polarity as the next theme. In a loose structure, a dot represents an unpaired valence electron. Because it belongs to the atom's outer shell, it can interact with an electron from another atom and form a covalent bond. Inner shell electrons are not shown, since they generally do not participate in bonding. The correct answer is that nitrogen can form 3 covalent bonds and be directly surrounded by 3 atoms. Its Lewis structure shows 3 unpaired electrons available for bonding, along with 1 lone pair. That lone pair can occasionally form a 4th dative bond, as in ammonium and H4+. The correct answer is 8 electrons. Each chlorine atom has 3 lone pairs, contributing 6 electrons, plus 2 share in the covalent bond. Together, that makes 8 electrons around each atom, satisfying the octet rule. By bonding, chlorine reaches the stable electron configuration associated with argon. Great job! The correct answer is that nitrogen in the ammonium ion has the electron configuration of a noble gas. By forming 4 covalent bonds, it is surrounded by 8 valence electrons, satisfying the octet rule and achieving a stable configuration like neon despite the ion's overall positive charge. The correct answer is as far apart from each other as possible. Electron pairs repel one another, so they arrange themselves to minimize that repulsion. This is the basis of the VSEPR model, which predicts molecular geometry. Lone pairs repel more strongly than bonding pairs, influencing shapes such as water's bent structure. For phosgene, the central carbon forms 3 bonding directions, 1 double bond to oxygen and 2 single bonds to chlorine, with no lone pairs. The molecule is trigonal planar, with bond angles near 120 degrees. The double bond slightly changes the angles, pushing the chlorine atoms farther apart. Well done. Excellent answer. Electronegativity is an atom's ability to attract the shared bonding pair of electrons toward itself. It does not simply mean forming a bond or achieving a noble gas configuration. This distinction is fundamental for understanding bond polarity and how electrons are distributed in chemical compounds. Excellent answer. Chlorine is more electronegative than bromine because electronegativity increases from bottom to top within a periodic table group. This trend describes how strongly an element attracts electrons. It's also worth distinguishing electron affinity. Chlorine releases more energy than fluorine when gaining an electron, despite fluorine's higher electronegativity. We consider this C = O bond. Because oxygen is significantly more electronegative than carbon, it pulls the shared electron cloud toward itself. The bond is polar. Oxygen carries a partial negative charge, delta minus, while carbon carries a partial positive charge, delta plus. This polarization makes carbon especially receptive to nucleophiles. Well done! Chlorine's higher electronegativity pulls the shared electrons closer, making the HCl bond polar, with partial negative and positive charges.